haven't, ever. So at least once in your life, you used map or filter or reduce, and you know that there is a concept of higher order function. In general, is a concept of a function which takes another functions and does something with this. Okay, so with a given, for example, collection, context, or whatever. So it was back then, 6 years ago. It was quite clear for me because I used only Python, which has kind of not very fun lambdas because they are only expression lambdas. But I used map filter reduce before, so I knew, okay, this does this. Okay, but continuation pattern style was new for me, and actually this wasn't everything because there were these weird constructs: char, cdr, cons. How many of you know what this is? 1, 2, oh, many, yeah. Last one?
Yeah.
So last one is?
Construct.
Yeah.
You can construct a list, but no.
Yeah, it's great. Yeah. You can construct a list. In Lisp, the language, lists are very important constructs. You know, they are basically one of two things of which language consists. I mean, lists or S expressions and parentheses, as you know, many parentheses in list. So a constructs a list. It takes one cell, as we call it, and appends to the list which exists and returns any list. Char and cdr, actually, you may know under another name because they were invented in 1950s. It's in programming world. It's prehistorical times. You know, 1950s. Later, then were named in another languages like head and tail, or first or rest. So now it's quite obvious what does it mean. Actually, it's a kind of abbreviation, contents of a address register and content of a decrement register. When Lisp was invented, there were these very, very powerful computers which has some kind of few bytes of anything, you know, random access memory or anything. So these were actually names of the register to which a construction of list was which was using. So char, cdr is head tails. Okay, so it's quite clear. We also used some kind of thing called Y Combinator for anonymous recursion. So actually, when I saw this first time, I scratched my head and I thought, what am I doing here? I will, if time, I will tell something about the Y combination later if the time is okay, because it's an extra for this talk. Do you know what Y Combinator is? I mean, not the site which helps the people to start the Y Combinator as a higher order construct. How many of you?
This is from thread calculus. Yes,
yeah, it's
function. It's take a function.
Yeah, you are correct because it's a fixed point combinator. Exactly. Yeah, so and this is the actually earlier we passed on the mathematical, you know, part of the computer engineering, but this is the fully mathematical explanation for this. Fixed point combinator. It's a fixed point combinator, meaning that it's the function which, for given argument, returns the same argument, and the Y combinator has an argument of function. So the function which takes the function and returns function doesn't make sense. Actually, I wasn't going to explain it now. I will explain it later if you want, because it's kind of funny when you know something about this and can use this. This thing in parentheses for anonymous recursion. Do you have any idea why would we want that anonymous recursion?
Recursion lambdas.
Yeah, exactly. And we don't want to name things. Mm-hmm. Yeah, so we don't have name for the function we want to recurse over. We are good.
We avoid two problems of the hardest things in the computer.
Yeah, I told this how this area went here. So move on. Map. It's a map implementation. Simple map implementation written in JavaScript, as we can see. Nothing fancy here. It just works. And You may wonder why would I put it here. I put it here because it's actually a code from our application, because we were unified, which allowed us to unify a logic of making things in the part of front-end and backend. I mean, we had map in JavaScript, and we had map in Perl, and we didn't use the language specific maps. I mean, in Perl there is in JavaScript first there is this map function in an array, which does basically the same what this does. This is actually definition, this is the usage, and this is the native JavaScript map operation. It's kind of similar. In Perl, this is our implementation, this is our usage of it, and this is how could you do this in Perl. Succinct, yeah, isn't it? Concise. Nice, but we decided, I mean, our senior programmer decided that this is concise when things are small, but usually the subroutines are getting bigger, and this is an implicit topic variable. Bro, it means a lot. Its value is
succinctly said.
Yeah, its value is actually something that is something like this in JavaScript, but in many ways. I would say more clever and more obvious. Yeah, sure. So this actually does the same thing, but we decided that we have our own implementation of map. We pass the subroutine and name the argument. This was actually an exceptional rule, because if the subroutine was 3 lines or longer, we named the parameter. If it was just 1 line, we could just skip this and use the shorter version. But basically, we decided to stick to some style. Okay, so this is map. This is for each. It's quite simple. It applies a procedure, subroutine function on each element of the list. This is usage, and this is how can you do this in Perl. Obviously, actually, if you are a C++ programmer, you may know this construct. You know, it's quite obvious. Few things about Perl syntax. If you didn't notice, Perl uses sigils. $sign is a scalar. It's a scalar variable. For as a construct is quite similar to any for any language. Say is just a shorter version of print with a line ending. So Perl guys thought print and then print a new line sign is quite long, so we just would say no echo, no something, just say it. So actually, because it's Perl, you can do this. Use the implicit topic variable. Don't declare any. Oh, yeah. Don't declare this variable because it's used here. It's just repeating yourself. So you can do this, and because this is Perl, and you can just. I said that this is an implicit topic variable. So why do we have to be so explicit about this? We don't. We just can do this, and because it's Perl, it's actually quite big, isn't it? You can use what?
Yeah, yes.
No, yeah, you can use just postfix suffix for prefix. I mean, no, you can put a for statement as a postfix. I would say postfix to an expression, and it would be done just for this arguments between 0, 1, and 3.
So to be rigorous, it is still too many signs because you have a semicolon.
Actually, the space here isn't necessary either. So yeah, but we didn't use that because it would be a mess. So we had our standard. But Okay, this is few things about Perl. Actually, this for stuff is taken from another talk, which explains what is TeamToady. And you know what TeamToady means? Besides Tomek, it's a Perl mantra, Perl motto. There is more than one way to do it, which explains a whole bunch of stuff in these previous slides and how can you do these things differently. So, Perl uses TeamToady. Perl allows us to choose what we use, and we chose, as we saw, some utils or map for each and another stuff. But you may now ask, you came here for continuations, and where are they? So, when I was researching this, the stuff for this talk, I came for few terms which I thought were quite similar. And I want you to point me at differences between this. What can you say about these four things? Anyone want to say about something about closures? Are closures lambdas? Yes.
No.
For example, yeah, it's kind of hard, but closure is main lambda with a context, I would say. Yeah, some context. Many languages are not strict about naming things and naming things closures when they are not closures, and naming things lambdas when they are not lambdas. But closure is roughly lambda with a context. So you can do closure, for example, which increments the value because it captures the value of the, for example, counter from another scope and increments it having its scope. And so, okay, closures. Callbacks. What callback is? Is it function? Okay, it's safer words than lambda. Okay, can callbacks be lambdas?
Maybe more like closures.
Okay, so maybe closures are callbacks?
Yeah, okay. Let's say yes.
Okay, we'll see, because there are two more things I found. Continuations are weird continuations.
I'm here.
Oh.
No.
Okay, but I would want to hear it from you. What do you think continuation is? Maybe even if you know, try to explain. Okay, so
It captures everything when it's being instantiated.
yeah.
And then when you call it or something, you will go back to the continuation and continue the execution from there.
Right. So is it a closure?
As well, it's also closure.
So
It captures.
okay, so is closure a continuation?
Not necessarily.
Yeah.
It may be used as well.
Yeah, I had the same problem. You know, is closure a continuation? Is continuation a closure? Wait, if continuation captures the state in which was initialized, so is it a closure, like a counter example? The example with the counter I gave you. And what's more, there are also coroutines, which are
Some kind of routines.
Coroutines are an idea, at least I know that means very well. Idea to actually have a smaller function, something perhaps smaller than a function in a procedure that can execute parallelly with less context switching or less burden. This burden context switching. So that's the idea I know. Okay, the full answer.
yeah, the answer is actually correct. And if you heard Tomek's answer, do you think coroutines threads? Do you mean threads? Is it quite similar?
Or do you know where to switch the context?
Yeah, sorry.
In coroutines, you are deciding where to switch
Yeah,
the context.
exactly. So coroutines are, I would say, cleaner than threads because they decide where to pass context, and it's actually symmetric. I mean, you can pass and be passed even. And threads are actually made for something different because coroutines actually are sequential, I'd say, in the sense of not being able to be used in multi-threading environment, because if you pass a context, you must be sure that the context is still valid for a given part of time. So, Konrad, do you see anything similar with the stuff you do for a living?
Yes, I could argue.
Yeah, because
I like to have a context. It's true, but it doesn't really have different reactors. And that is a bit less.
yeah, I would say so, because when I read this, and also I read things like continuations are in functions, coroutines are a bit like threads, but not like threads. Continuations are similar concept to an actor model. Callbacks are used as closures and vice versa. You know, it's kind of confusing. And the difference is actually, as we said, closures, lambdas with context, simple concept, and are always functions. Closure is a function. Callbacks is also a function, but in the example I gave you earlier, map and for each, map actually, no, it's not example. For each example, callback is the function you pass to the for each is invoked at some point. Okay? It doesn't actually have any, it doesn't have to have any state assigned to it. It could, but it doesn't have. Continuation is something we'll talk about. And coroutines is this kind of thread-ish, actor-ish something, which also is in the function, actually. It's an object. But these are all similar concepts of one thing, passing a state and behavior in your program, in logic. So, continuations, what are they then? Let's talk about JavaScript again and do some easy stuff. It's from the presentation here. And these are these few things. We involve something on argument string and concatenate with another argument. We have this result. People capitalize to on this result and do a console on it. It's quite simple, and the logic is like here. This is a main program. It passes the arguments to concat, then returns and capitalize, return, console on. Okay. And what does continuations do in this particular example when you use continuation passing style? So concat is same definition, but you don't return. You use a continuation which is passed as an argument here, and invoke it with a result which is a result of this function. Okay. Then we have capitalize, which also takes a continuation and invokes it with the result of this computation. And we invoke this in this manner. Arguments, continuation. In the continuation, we have another function which takes this result and takes it from there, and have another continuation which passes the whole result of to the console log. Okay. So anything. Oh, and I will show you the flow for this. It's main program passes something to contact, which now passes something, the result of it to another context, another function here, okay, function. Now uses some logic, does some stuff, and invokes another continuation function, and invokes some stuff, okay? So you can see the flow is kind of uninterrupted. It's simple when you see this. But I think I should have the slide here. Okay, so move on.
My question is,
yeah.
What is the difference between function composition? If I get the functions and I compose them on flow,
It's similar.
You mean specific language or?
No, for example, in JavaScript, when I compose function, I call f of g of h. Some
I see. At some point, you have to touch a stack, and that will be a problem.
Stack is a problem, but mainly you have to return a result of a function. And here you don't return. You invoke another function. So this is a difference. Conceptually, it's the same.
Console log has some side effects.
Oh, yeah.
Chicken.
Yeah. It shouldn't be there, but it's maybe exactly. So basically, the difference is the return statement. The return statement used in normal functions when function returns. It's like this. Here you have the continuation, and the flow is like this. Because actually you could think about this as a composition. This example.
Exactly. That was my question.
Yes, so this is a composition flow, I would say. It's quite common. So we used this, and as I said, this is actually an answer to your question. In continuation passing style, you never return, just never, ever. And this is the hint. You can treat a procedure, a function, as a return construct on which you invoke the result of the computation. So, as I showed you. So let's practice and have this piece of code return to the continuation passing style. How will you do this? This is JavaScript. I thought JavaScript would be the most well-known language. So how would you do this? Any ideas? Just about.
So in place of return, you have to solve the continuation of x.
Yes, so in place of return.
And the continuation of x, and continuation is an argument of function.
Yeah, exactly. So this is our identity function written in continuation passing style. It's quite similar to the return version because you could write, for example, something like this. You couldn't write return because JavaScript has keywords, but for example, that is quite similar to the concept. So yeah, it's the way to go. Basically, in some examples, you could have this CC for a name for this variable, current continuation. We will return to it later. So, where do we use continuation passing style in real life? Because besides the web app I was developing, so actually we use continuation passing style in asynchronous calls, for example, in JavaScript, for example, when you have some site and you want to just have an Ajax request and have some data from it and do some stuff. So it's basically taken from the jQuery tutorial and jQuery documentation for the post function. So very basic. What it does, it doesn't return. What it doesn't, it doesn't return. It has an argument, a site we want to access. It has this function, a continuation in this continuation passing style environment, and we have the result of some computation done by post some time in the future. Okay, so we take it and append it. We also use continuation passing style in non-blocking environment. For example, in Node.js. It's also taken from the documentation from Node.js. What it does, it reads file asynchronously and invokes a function with two arguments, error and data. Error is not empty when there was an error, so you draw it and console log the data. It's quite obvious. But how do you rewrite this to the continuation passing style?
Some kind of card. So
no, I mean, like the previous example, you just you could define the myFS read file CPS. The first argument is the same, but we can add arguments for error and argument for data. And what would this implementation of the function does? What it does is when the error when there is some kind of error, instead of invoking this function with two arguments in first null and second null, we can invoke this particular function, which will be our error callback or error continuation. It will do something with an error. And if there weren't any errors, we could just use the continuation for the OK scenario. Just, for example, data. So what we can see here is actually that we have two continuations. So you might wonder now that it will get messy when you have the real size code. When you have this part of logic, it can involve something for error and something for not error. What's more, you can have many other continuations or functions, processing arguments, which can be invoked, for example, when we have not valid session, when we have user deleted, when we have user who has too many concurrent sessions. We can invoke each of the, we can write a function which will invoke particular continuation when it would be suitable for it. So you might wonder if it would be messy. Yeah, actually, two isn't the limit, as I said, because you have this many functions you can call or not. The implementation decides if the error callback is called or the normal callback is called. But actually, when you saw this, the flow of program, for example, stack trace, you'll see that each invocation is straightforward, I would say, as you saw in this image when the flow was written. So, okay. And since I'm talking, it's the perfect example of continuation passing style when you don't have any return and treat any mathematical computation as a function. Okay, so it can't return. So adding something, multiplying, squaring doesn't return. So we have these three functions defined with another argument continuations, and we have this kind of construct we could argue if it's readable. So what's the problem actually here? Anyone? Any idea what's the problem? Suppose we want to. It should be multiplied here. No, it's okay. Multiply. Okay, no, it's good. What's the problem here with this shape? Yeah, pyramid of doom, it's called. So, what's the solution? For example, in JavaScript?
Promises.
Yeah, promises. Have you heard about promises? Promises basically just allow you to return a value. Return a value which will be computed in some time in future. And when it will be computed, you can just pass, you can do something with this. I actually used the promises for JavaScript lately, so it doesn't do this. It does kind of it looks like synchronous calls, but there isn't, of course, because you can have this promise and invoke the promise with the callback, which will be have the promise with the callback, which will be invoked when the value is ready. Yeah. So the problem is pyramid of doom, but there is another problem, which is, for example, in JavaScript, when if you have this many calls function, function. And if you add, for example, recursion, you have function, and you have this stack overflow problem. Because JavaScript also uses stack. And so what's the problem with the stack? It's not as big as any functional programmer would want, for example, in JavaScript and Perl. There isn't something which we call tail call optimization. Have you heard of tail call optimization? So basically, we can avoid this. But in the web app I was a part of, the project web app I was part of, used Perl with JavaScript, used the kind of constructs I showed you earlier, and it didn't actually have any tail call optimization. So, but it worked for us, so it was good. But tail call optimization, I would like to be specific, because tail something, these are not the same things. And once again, please, who can tell what is tail recursion and how it's different from that?
What's the most limited case? You call yourself,
Yeah, so tail call is basically,
you can call another function.
yeah, tail call optimization.
In place of the stack.
Yeah, it's basically a term for saying that the language, as the language itself, as a means, as implementing, as tail call optimization implemented. For example, when it sees tail call, it can optimize it somehow. And
you will notice that you're not using any other variables or data on the stack frame.
yeah, so basically, you don't create any stack frame, any other stack frame. Yeah. So as we said, tail recursion is when you. Oh, it's not. It's not a tail recursion. Why?
You have to rely on
Why it isn't tail recursion? Because of this?
No, you need to do the multiplication after computing.
Yeah, of course.
It needs to have all the intermediate values in memory before returning.
Yeah.
The whole chain.
This is a problem. This is not tail recursion. Oh, let's say table. This is the problem. This is not the last statement here, because the multiplication is done after the return of this. This is actually, I believe, a proper tail call, tail recursion actually, because then you have this factorial, tail factorial, which has accumulator value, which it will return when it's 0, or invoke itself with some another argument, but basically it's the same function. So as you said, we can just not create any new stack frame and use just swap arguments and we invoke the function. Yeah, so this is tail recursion. This is tail call, but basically, as we said before, this is also tail call. This is simpler case. And what does tail call optimization? Just to show what's the difference. The language itself, as I said, can optimize this invocation, the pyramid of Bloom fact and stack, into this. Because when you have this function invoked as the last thing, you can the language can swap it to the iteration, simple iteration, which basically doesn't create any new stack frame, just increments some values, does some stuff with the arguments, invokes itself with another argument, and then returns. So, as you can see, no parameter doing here, and it's not because of promises. Promises didn't solve the problem with the stack. Tail call optimization would solve the problem in JavaScript, and it will be solved if you are curious in ECMAScript 6, which will have tail call optimization. One more thing, because we were using Perl, once I thought, yeah, we have this problem with the stack, possible problem in the stack. Maybe we can just optimize tail calls by ourselves. Just do it for the compiler because it doesn't do it itself. And actually, it did. There is a module, because in Perl there is also a module, the module in Perl, which allows us to invoke a function as a tail call. It's not a valid use case, it's just one line. Basically, we can just write a factorial and invoke tail, name of the function, and new arguments. It would not create a new frame, stack frame. It would just have swap an argument. Okay, so this is the syntax for invoking object methods as a tail call. It could be done in Perl, actually. It's quite simple. But as we are here, and we see that this is where this is going, or done. What is so? If we are not creating new stack frame on the low level, when there is this function, it has beginning and the end, and it has an argument. What's done under the hood? What do you think? It's actually a jump from this part of there is this function, arguments, blah, 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 something, tail call, jump, swap arguments, do it again. So it's actually, it's a go-to under the hood, but in the tail call. And Perl isn't lying about that, because you can, this is the module, and you do this, this is the same, but this is the pure Perl without any modules. This is nice stuff. What you do is basically, remember when I told you about the sigils? $$ is a sigil, @ is a sigil. It shows you this is the list, and the list variable, it's named blah. Assign the value of these arguments to the default list, these arguments actually, and invoke the function subroutine with goto. And it does not lie, actually, because, as I said, what it does, tail call optimization and tail call optimized to this is just goto. Yeah, do you agree? So basically, when you talk about functional goto, I mean, in this particular use case, it's not that goto, because you don't do this by yourself. If the language has tail call optimization, it does it for you, and it does it well. So basically, I didn't decide to use goto in my code. I actually let the stack to grow, and it's okay when you don't have many new clients, you have stable application. It does work, and it's working actually up to today. So yeah, it's good. So basically, I said earlier about hierarchy functions, map for each, how they are invoked, fallbacks, how continuation passing style is used in Ajax in non-blocking environment, and how tail call optimization can help with growing stack. So have we said everything about continuations? Actually, we didn't, because as a concept, continuation isn't even a function. I showed you this callback closure continuation coding stuff, because actually they aren't similar, as Konrad said. They are similar concepts, but they are different. So what are continuations? Continuation, in definition, actually, is an abstract representation of a program state. So basically, just what you said, and it was defined as a concept in 1964. So it's also quite old. Oh, it's 50th birthday. It's 50th birthday. So, and what can we say about continuations? That is that we talked about continuations, meaning continuation passing style, which is using a continuation in the function to do the specific flow of program and growing the stack in the JavaScript, because if we were using scheme for this implementation, we wouldn't have the growing stack problem. But we were using that. So, by the way, we were talking about this, the continuation in this sense. But there is a first-class continuations is what is actually implemented in Scheme, as I said, and Haskell, for example, let's say some specific model, but models Haskell, whatever. And what's interesting, Ruby has first-class continuations, first-class citizens. It's as I read about this, it isn't very. The Ruby developers aren't very proud of the existence of it, because the whole concept of continuations looks like a bit of academic concept, because we have this normal language which has return. So basically, why would we want to have this continuation argument everywhere? Because in the web app I was developing, it was basically something like function continuation, error callback, normal callback, and the callback which is invoked here, okay, but it also accepts an error callback which is taken from here, so pass it here, and again, and again, and again. So when the error callback is invoked, it actually does something like this, going up to the place where it was defined, usually a few thousand lines after or before the invocation, actual invocation in the code. So the difference between the two concepts is actually quite big, because this is a continuation as a function, this is the continuation as a abstract concept. So basically, it's the example you gave earlier, because continuation sandwich was a mental exercise, I would say, introduced to explain what the true continuation is. So, for example, imagine that you're in the kitchen and you're staying in front of the fridge, and you have the continuation, and just grab it and stick it in a pocket. You open the fridge, have some bread, have some butter, have some cheese, I don't know, whatever, and do yourself a sandwich. The sandwich is put here on the table. So what do we now? What do we do now? We have our continuation, we invoke it, and what we see? We are in front of the fridge, we want to make a sandwich. We open the fridge, but there isn't any ingredients. There aren't any ingredients. What actually happened, we invoked our continuation, and we have our sandwich here, done. It was made by a previous pass, previous pass of the continuation function, I would say, but the continuation itself is something we can, for example, press it. So basically, any Python developers here? Yeah, so generators, anything similar? Because generator is, I could say, it's kind of specific subtype of continuation, because we have this concept of generator which isn't the function itself. It captures some state, some context, and you'll send it, and it could be repeated. Yeah. So, but again, generators aren't continuations as such. Continuation is something which can have context and can be reset. So in Scheme, that was this call with current continuation, also called CC construct, which basically allowed first-class continuations to be executed with the saved state. And this is the part when I was wondering if I am talking, when you understand me. So basically, just ask if you don't. So for example, here, oh no, it's okay. So for example, here, yeah, we have Lisp syntax. What you have to know about Lisp syntax is the parentheses and so on. Okay, so there are many parentheses, but yeah, okay, be more specific. This is defining some function f, yeah, agree, which has an argument which is named return, and this argument is invoked with an argument true, and also this is an argument to, if you can, these are parentheses. Okay, so our continuation, when it is invoked with a lambda which returns itself, it's an identity function. Okay, so identity function. Display just console log. It's console log basically. When the function f is invoked like this, it displays 3. But when you have this, when you apply this concept of call with current continuation, call CC and abbreviated, it displays 2. But why? And one hint, this actually could be named sum. Because, as I said, the return in Scheme doesn't exist and isn't a keyword. But what it actually does, it's when the continuation is put out of the pocket and invoked, and it returns a state which was it was saved and created. So basically, this state, not the regular. It could be changed because you can just adjust your state, just as you do with closures. You remember closure, the function or something with the context. But this, as a first-class construct in the language which supports it, just allows to save a context. And how could be used, for example, in the real world? And by real, I mean Lisp. Yeah.
You, for example, implement exceptions like in C++ style, but as a library, modifying the language.
Yeah, exactly. So exceptions, because of course the whole syntax and whole goodies of Scheme and Lisp are these things too. Yeah. There weren't any exceptions as a construct, but they can be made with the call with current continuation and first-class continuation support, because you can just imagine when you have this state of program and you throw a exception continuation with the context. And it is actually, from the very high point of view, exactly what does Java, for example, throws an exception. It suspends its normal run and just invokes some kind of language construct in Java, of course, obviously, with some kind of context, stack-based. And you can just see what, for example, what of the output. And so basically the continuations as a first-class citizens were, because they were in Lisp invented as a part of the language and first-class citizens, were used to define almost every kind of control flow in the language. Because control flow is what continuation is about. It's part from this image I showed you earlier with the normal flow versus CPS flow. You can just have the flow just as you want. And basically, the continuation, if it's first-class citizen, allows you to do that. As I said, we used only CPS, so kind of not continuation per se, but it was actually quite fun and quite annoying, I would say, because basically most of the time you just want to return. But if you're doing asynchronous, of course, yeah, it's cool or something like that. But basically, that's what they are made. So continuations are just, I would say, abstract thing invented for a Lisper for a fun. And if you came here to know something practical, I'm sorry, but the whole presentation just is enclosed in this slide. That in particular implementation of this, or Ruby, and it's implemented as an object actually, so kind of different implementation. You can just create your own flow constructs without help of a language, and that's it. So thanks for watching. If you want, we have some extras. I don't know. Any questions?
How difficult was it for you to readjust?
You know, basically it was my first job, so it wasn't that difficult. I mean, if I was first a Java programmer for example, 3 years, it would be hard for you. But I think when you don't know about particular, for example, object-oriented concepts and imperative style of programming, it's easier for you to adjust. And basically, when I started, I knew Python, which allows both object-oriented and functional programming. Python is Python, okay, but it allows both of the ways of programming. So I could just translate what I was learning about the concepts in Perl and JavaScript to what I knew about Python, and it was quite okay. So actually, it was harder for me to make this presentation because when I read about the true meaning of the continuation, you know, which was the construct we used, we were supposed to do that, but didn't do because we used the wrong language, because our senior engineer wasn't able to use scheme on production, you know. It was quite fun, but very challenging, I would say. Yeah. Any questions? Any other questions? Yeah.
Yeah. Could you explain the Y combinator?
Oh yeah, Y combinator. Okay. I was afraid of this. So this was explained. Actually, it's, as you can see, it's first, last, rest. Construct figure or first tail in Perl because Perl. Y combinator. So back to the Y combinator. As we said, it is a fixed point combinator. Fixed point function generally it's the function which on given argument returns the same argument. So for example, a square function has a fixed point of 0 and 1 because square function from 1 is 1. Square function from 0 is 0. So the Y combinator is a mathematical concept which can be implemented as mathematical concept, I mean Lambda calculus, and it can be implemented to have a function, fixed point combinator function, which takes a function and returns or invokes itself. So, no, itself, the argument, because this is the Y combinator. Basically, this is the definition. Yeah. So, I mean, I don't expect you to just sit here and analyze it because it took me about, I don't know, 2 or 3 days to first read this, then know what it does, and then find the examples of usage and see how they actually are doing. Because when you see the definition of this function, it's a mess, you know. But when you use it, I don't have any usage, I think. But if you use it, it's kind of nice. I try. Okay, so we have this subroutine which does what I said earlier, mathematically, theoretically, and we can invoke it. Okay, so we can invoke it with some okay, we can use Perl. We will use Perl. Okay, we don't mind. Okay. To be easier, let's take some array. Array. And for example, we won't use continuation passing style and we will use return. Okay, is it okay? Okay. Because it would be two concepts mixing and it would shadow. Okay, sum. We could implement sum. For an array, for given array, we have we could implement sum. First, this is not a proper argument because this is our recursive function we can use. It doesn't really have name. It does here, but it could be something. We don't have to name it because we know from the construct of Y combinator that this is the function we would use for anonymous recursion in the body of this subroutine. So, okay, so let me use my normal editor. It would be faster, more faster. Okay. Do you see anything? No. Okay, so if you want to see, maybe more. So we have this sum we want to have from the Y combinator, and what it does, it basically takes a subroutine which has one argument, a recursive function we use, and it returns a subroutine. So far, so good. Oh, it's not clear yet. And it returns subroutine, which does something. And it has an argument of an array we will later have. And it returns, depending on if array is, let's assume we have array function. Depending on if array is empty, it returns a sum. Okay. Or it will recurse part of array. And also, we have two things missing.
Shouldn't we return a 0 in the first place?
Actually, it depends what we are doing. If we are having, we are summing now. Okay, so we are returning sum. The sum is an argument accumulator passed here. We will return it. First argument will be sum, will be footer, or as we can call it, tail of array, and okay, so basically, for each array which isn't empty, it recurs itself with the tail of array. So, for example, if it has 3 elements, the tail is 2 last elements, and the second argument, the sum plus previous sum, with the head or contents of the first element of array. But we didn't invoke it yet. Now we invoke it, so we invoke it with, for example, let's 0, and this is the place we use 0. Let's do it for you. So basically, Y Combinator returns a function. Yeah. So here is the return function we are now invoking anonymously because we don't like to name things, as I said before. Naming things isn't necessary when you use the thing one time, because basically we could do something like this. We could do it probably is more readable. It definitely is. Define a function with just a Y Combinator returns function, okay, and now we invoke this argument. What it does, it recurs over this argument, which magically is the function here, but we can use it because it's the outer scope of the previous function. So, as I said, it took me a few days to actually read the definition, read the examples, and implement the first Y Combinator usage myself. So, sorry, but it's not obvious, especially when you are, for example, not using. If you have never heard about Lambda calculus or something like this, it's not very obvious. But now I think maybe you can see some differences to normal recursive approach. The differences are that there are many functions, subroutines passed around and returned, and the result of this is somehow the sum here, the sum of the function of elements of this array. So yeah, so this is the full example. Particular variable. So I showed you. Any questions?
No, think about it more.
Yeah, so basically you can just read about it, but I don't encourage to read too much because on Wikipedia there is this, I think it's some kind of, because Y Combinator is a generalization of a U something passed to the, mathematical stuff. I tried to read, but after a few lines I passed. I could just show you that. Why? Actually, the usage is the not this. So yeah, basically this is the definition of the curve. It's very many stuff. Yeah, fixed point calculus, there are some. So basically, if you see some patterns here, this is a function we are using. It has some name given by the argument of some kind of magic function passed to the Y Combinator, but this is the function we use. We can invoke it, and if we know the recursive approach to the problem solutions, we can just apply it to this, but we must remember that we have some kind of terminal operation, because the as I said before, I didn't use continuation passing style because it would be just more shadowing the whole point, because we could use just continuation here to pass third argument. It will be here, continuation, and involve the effect or radius. So it will be instead of return. It will be the same, basically. But the Y combinator itself, it returns inside of itself. It's you know, we used the Y combinator because we have a value to space, actually. For example, in for each, if we don't use the native form of the language, we don't have such things like break or break, So we use the functional approach of for each with the callback. So we could just, for example, throw an exception and just catch it outside. The job we want to, which solve the problem exactly the way we want, because we have some kind of loop defined by ourselves by recursion, minus recursion, and we can just pass some error callback and callback, which could be invoked in any situation inside the actual logic of our function, which is an implementation of it solves the problem we have. So we have the value to space, and we have for. And we want to have some kind of exit arrangements, exit possibilities. Yeah, that's all. Yeah, any other question about anything? If not, thank you for coming and that's much practical stuff. Thanks.
So guys, as promised, there are prizes. So if you would be so kind and to open a random or
Bye guys.
thank you.